In this video, I'm going to go through question 3 on lesson 8-2. It says, the scientist is studying the population growth of a certain type of bacteria. The function y equals 50 times 2 to the x power represents the amount of bacteria in a dish x minutes after the scientist started a timer. Part 8 says, determine whether the function represents exponential growth or exponential decay. Since my base is a 2, it's bigger than 1, I know that this is going to be an exponential growth. Now I need to graph the function. You can either draw a coordinate plane with this. If I were drawing it, I would actually just use mainly quadrant 1. I would put a little bit into quadrant 2. But I think right now the easiest thing would be just to use our graphing calculator. So if I grab my graphing calculator, I already have the function put in here. So I have 50 times 2 to the x power. And I'm going to change the window settings. So I changed my window settings to the x minimum at -5, the x maximum at 10. The scale is just counted by 1. Now you could adjust those however way you want. The x is referring to my time. So in time in minutes, I don't need to have a long amount of time just to see what the graph will look like. So that's why I kept it at 10 and the minimum -5. So the time, I can't have negative time, but in this case, for this particular problem, a negative time would be the time before the timer starts. Because remember, it says up here, the x minutes after the scientist started a timer. So this x right here represents the minutes after he starts the timer. So there's some time before it. It's just going to be represented by a negative number. My y minimum is going to be 0 because remember our asymptote is a boundary line. And the asymptote lets you know that for an exponential, you'll never cross the x-axis, which is where y is 0. Y will never ever become a 0 because you can't raise a base to a power to make it equal to 0. So I'm going to keep my y minimum at 0. The y maximum, I don't know how big the population is going to be for bacteria, so I just put it at 500. You could put it as 100, you could put any number, but it has to be bigger than 50 so that you can see it on your graphing calculator. And then my scale, my y scale, I'm just counting by 50. So now if I hit graph, you can see my graph here. So as I go to the right, as the time increases, so does the number of bacteria. So now I need to identify the key features of the graph, and I have the five main ones that I want to focus in on listed below. So the first one, I'm going to do the y-intercept first. The y-intercept is where it crosses the y-axis. And when it crosses the y-axis, your x is 0. So if I put a 0 in for x here, 2 to the 0 power is 1. 1 times 50 is 50. So my y-intercept would be 0, 50. And this is just saying that the bacteria was at 50 when the timer starts. Now, if I do the domain is talking about what are all the kinds of time I can have. Because if I go to my graph, it does continue going to the left and stays above the x-axis, and it continues to go to the right. I know that the domain is all real. I can put any amount of time, the time before the timer starts and the time after the timer starts. I can put a number in there and it will tell me what the population of the bacteria would be. So this is all real numbers because, see how I'll put that, it represents the time before and after the timer. So if I had a -5, that means 5 minutes before the timer started, this is how big the population was of the bacteria. Because remember, the scientists put the bacteria in the dish before he started the timer. Then he started the timer, and then you would see that the bacteria grew. Now the range, if you look at our graph, so if I go to my calculator, it never goes below the x-axis, and it never gets to 0. So the range for this one would be, and if we're talking about like if we're talking about the time after the timer started, we would start at 0 and go on. So that would start at 50. So even though that it can start at 50, it could go below, the population can be below that, but it always has to be positive. So these, and I can't have part of bacteria, it has to be a whole. So this is going to be all whole. All whole numbers. And then the explanation would be all whole numbers. This would be bacteria is always positive. Just meaning that it's above 0. Okay, now somebody might say, well, shouldn't it be like after the timer starts? Not exactly, because here you could go before the timer starts and you would still have a population in there. So we want to just make sure what is the total population of the bacteria from the very beginning to the end. Now the asymptote, this is just y equals 0, meaning that it's always positive. You can't have a bacteria ending up with a population of 0. And then the end behavior for this would be as time increases, bacteria increases. And as time decreases, the bacteria, let me erase that. Bacteria approaches zero. Now the domain and range, those are going to vary based on the word problem. So you have to think, when you're talking about the x coordinates, are there limitations? So in this one, there is no limitation for the time, because they're saying the time is before and after the timer starts. So that means it could be any number, positive and negative. The range, there is limitations. It can't be negative numbers, so it's always going to be a positive whole number. And I can't have part of a fraction, or part of bacteria. So that's why I'm not going to say all real numbers, because all real numbers would include positive and negative, fractions and decimals. Okay, so you have to read the problems very carefully to determine, are there limitations with your x and your y coordinates. Hopefully that helps you a little bit understanding how to find the key features of a exponential graph.